Yeah, okay, let's get this show on the road. So unfortunately, or maybe fortunately, I try to keep it because you usually have different people that you talk to, so I kept it like low on technical details. So it's not going to be a lot of Rust, but I have a link where I can show you the repository with the Rust code for this presentation.
Sure.
Okay, so without further ado, like a small introduction. So I'm a software engineer, like probably many of you. I have a small kind of a one-person consultancy, but I work with some different people. But my background is coming from scientific data analysis and from research specifically. I was right from the get-go, I was working with the large amounts of different types of data, including but not limited to genetic data. And we were working with a lot of OO frameworks and languages, but I quickly got into functional programming and functional languages, specifically Clojure and nowadays Rust, just because it's kind of when your problem is in your domain is about working with data, then you quickly get this win of not wrapping and hiding the data as objects, but working with it directly. And especially Clojure was a huge win right from the get-go. And today's talk is based on some work that I did that I think nicely combines these two concepts, so both data analysis and working with functional programming. So maybe before we dive a little bit deeper, a bit of an introduction. So why do you even want to employ recommendations or recommendation engines or recommendation systems, however you want to call them? Why do you even bother? And I was thinking about it some time ago, and if you go back to the 20th century or even like the beginning of the 21st century, then when we talk about some type of product, then you have kind of two choices, right? You have something that's mass-produced, but then this is like a one-size-fits-all solution for everybody. And then you have custom-made, like made-to-measure expensive things. So for example, for clothes, you can have a cheap suit from Zara made from polyester, and then you can go to London and have a Savile Row custom-made expensive suit for you, right? But what if you could have a combination of these two, right? What if you could combine the personalization of the custom-made product with the low cost of this mass production? And if we talk about digital products, then all the ingredients are there, right? We collect enough data. We have the tools, we have the hardware, we have the algorithms to do that. We can transform, analyze them, and we can create these much more personal and quote-unquote human experiences with these products. So the key takeaway here would be that you can have not just one product, but you can sort of tailor it so that it's one product for each one of your users, or even because these tastes of any given person change throughout the day, throughout the course of his life, then you can even increase that cardinality even further, right? And that's what these systems, recommendation systems, allow you to do. So maybe let's take a look at some success stories. So that's a pretty good example because we're going to probably interact with one of these today. So if we talk about Netflix, then this is definitely a company that's obsessed with recommendations. So for example, they regularly make competitions for data scientists, and they pay millions of dollars to the teams that can improve, even marginally improve some of these metrics that they use. Then another one is Amazon. Amazon, interesting enough, is one of the pioneers of employing recommendation systems, and to this day they actually run a specific flavor of these recommendation systems that's collaborative filtering. And their sole goal of the systems that they employ is to increase the average amount of the order value. That's what they optimize for. And then finally, one company that really gets this right, and TikTok, which is an unprecedented success story, right? It is equipped in one of the best recommendation engines in the industry. In fact, the whole company, you could say that it is the recommendation algorithm. So if you go back, for example, to the summer of this year, when there was the ongoing talks of purchasing TikTok by these, taking it over by these American companies, written by the Trump's ban on TikTok, then this is what everybody wanted to put their hands on, not the app, right? And nobody really, like this mobile app itself could be built relatively fast with a few freelancers on board, but everybody wanted to put their hands on the data and the know-how of how they're doing it, right? And now we can talk a little bit more specifically about one flavors of doing recommendations, namely collaborative filtering, which is a method of making automatic predictions about your user preferences, which combines two steps. So one step, this collaborative step, is collecting the data, and then the filtering step is about using the data in a way that allows you to predict the interests of a specific user, given this collective cohort of all your users. And to make it even more specific, we're going to apply and showcase collaborative filtering on a domain of a type of video streaming service like Netflix or TikTok, for example. And then the question that you might want to ask is, of all the videos that I have in my database and my application, what is the best video to recommend to the user next after he has seen a couple of these? And then before making any predictions, you would naturally start by collecting the data. And the problem with the data is that often it is very untidy, right? Usually we work with events, like which come in various forms and shapes, but usually they're very raw. But if you look closer at events in a type of video streaming service, then you quickly can see some patterns, right? So you're gonna have your entities, you're gonna have your users, you're gonna have your videos, and then you're gonna have some actions that that happen between these two, some interactions, right? So you could have a user watching a video for some amount of time. You could have a user clicking a like on a video, or maybe leaving a comment, or maybe like leaving a small tip for the creator of that video, etc. And then if you wanted to focus on one specific user and summarize that interaction, of the history of interaction he had with that video, there's various ways to quantify it, but one of them is by employing something called a score. So basically collapsing it all into just one single number. And there's many ways of doing it, but one way is by having a linear weighted combination of these different variables. And by weighted, I mean employing some type of weights that sum to 1, but also constructing them in a way that you put more importance on the things that you are trying to optimize within your system. So for example, if you want to optimize for user engagement or retention, then you would probably increase the weight by the time spent watching the videos throughout the day. Or maybe if you want to optimize for monetization, then on the videos that get more of these tips or more followers, right? You can even get more fancy than that and start introducing some type of back propagation where these weights are adjusted based on some type of fitness function, and your system starts learning from that and adjusting these weights throughout the day, throughout or even like on the longer time scales. So if we apply it to the whole cohort of our users and on all the videos, we can arrive at something like which is like a two-dimensional arrays where rows are users, right? Those are independent observations. So the columns are scores that they had, like the summaries of the interactions they had with these videos. And then we also have some missing data, which basically means that the given user has not interacted in any shape or form with the given video. And that's where you want to start making the recommendations. You want to start recommending the videos that these users have not seen, but you just don't know which one of these videos is like best suited to his or her preferences. And then we get into the filtering part of the algorithm. And now that you have these records of past user preferences, that you kind of want to see, well, how similar or dissimilar are my users, right? Which ones cluster together with the user I want to make recommendations for. So basically, you want to calculate the similarities between them. And one way of doing it is that something called person's correlation coefficient. It's just one of the possible measures of doing it, but it has one interesting thing about it. Is that the values of personal correlation coefficients are normalized. So they will always fall between a continuous spectrum of -1 to 1, where -1 would basically mean that these users are completely opposite in their tastes. 1 would mean that they correlate perfectly, and 0 would mean basically no linear relationship between these two users. And then if we look at the specific example of it, like a specific numerical example, here we have a handful of users, and we have applied this correlation coefficient to every one of them. And we get this pairwise symmetrical matrix of correlation. So as you can see, that this is 1 on the diagonal. That's because the user naturally perfectly correlates with himself. And on the off diagonals, we have the measures of the similarities. Some users, for example, here between Mick and Michael, we have negative correlation, so they're like dissimilar in their tastes. We have here very close to 0, which means they basically have almost no relationship. And then we have some users which cluster very close together, like over here, right, between Toby and Lisa. So we can now, if we want to answer the question, well, what video do I show to another user? We can, for example, focus on Toby. Well, you would take the scores as we recorded them, so this past collaborative part of the algorithm. We would remove the videos which he has seen already, and we also are not interested in the users that are negatively correlated with Toby. We would then look at how Toby correlates with these different users. We're looking at the positive correlations here, so how similar he is to these other users, and then we would simply convolve the matrix times this vector, effectively scaling the scores that these other users have with the measure of correlation. And the idea here is that these users which are closer to Toby in their tastes, which are most similar to him, they contribute more towards the overall score. So then by summing over the columns, we get the overall recommendations for all of these videos that we have taken into account. So we would, to Toby specifically, we would show TNL first, followed by this movie called Lady, and then the movie with the lowest score. So in this next part, I would like to talk a little bit about the computational burden of these correlations. As you have seen, the calculations themselves are not very complex, right? But the problem comes with the fact that we're talking about huge data sets. So for example, think about all the TikTok videos ever recorded and all the users of TikTok, right? And it even gets worse because these operations increase like quadratically with the size of inputs. But at the same time, they are what could be even called embarrassingly parallel. That means that they lend themselves to these highly parallel architectures like GPUs, which are very good at data parallel applications, even though they were initially designed for gaming and graphics applications. But people pretty quickly realized that they are fantastic at these types of calculations, these types of computations, simply because calculating one pixel on the screen or painting it very fast is pretty similar to matrix algebra operations. And used to be in past that you had to go through this tedious process of GPU programming. So you had to write the kernels for it. You had to, this was fairly low level and involved. You had to go through the whole ceremony of allocating memory on the host, on the device, copying it, invoking these kernels, copying the data back to the host of over the PCI Express bus. But fortunately, these days, we have a framework from Google called TensorFlow, and it kind of takes care of a lot of that. It has abstractions over a lot of these operations, and these abstractions can run on different devices, on CPUs, on GPUs, even on clusters of these devices. And they are conveniently expressed in a serializable way as data graphs of different operations that you apply to arrays, aka tensors, hence the name TensorFlow. Now, when it comes to deploying this into production, then there's of course many different choices. But if we're talking about performance, safety, concurrency, then Rust is kind of second to none. It's a language with one very unique feature. It uses something called borrow checker, which discovers the memory problems very early during compilation, so not during runtime, not in production. It also has no garbage collection, so which means it has a very tiny memory footprint during runtime. And all of these characteristics make it, in my personal opinion, a very good fit for this type of analytics, data, machine learning tasks. There's also a plethora of libraries for interacting with data, for single instruction, multiple data, type of parallelism. Also wrappers for working with TensorFlow and some other frameworks. Okay, so if we want to quickly summarize what we have seen, as I hope I have shown, then recommendation systems are fairly easy to build and to deploy. There's nothing magical about them, collaborative filtering especially. They are easy to understand. There are good examples of them out there working in practice, especially collaborative filtering, as opposed to, for example, neural networks can be a bit of black boxes. There are ways to get insights into how they work, and for example, TensorFlow makes it a little bit easier, but still, here we can kind of look into the soul of all these computations. But they also have some problems. Some of these problems they share with different methods. One of the main problems is the so-called cold start problem. That basically means that in order to make proper recommendations for a new user, well, the system first needs to learn something about his or her preferences. And it's made further worse by the fact that, if we go back to these first slides, and Netflix has this data on how very few tries you have to really get it right before user gets disinterested and leaves your platform. You get about 90 seconds to do that. So, for example, what TikTok does is they put these new users into a special type of feed, and they show them different videos, and they try to really quickly learn about the preferences of this user. Then another con is problem of these systems that they are fairly compute intensive. There are ways around it, like we've seen with offloading some of these computations to GPUs and other parallel devices. What Netflix does is they divide their cohort of all the users to about 12,000 different clusters, and they apply these recommendations not to single users, but to clusters of these users. They kind of reduce the dimensionality of the problem. And then there's a third problem, which is probably a little bit harder to mitigate than the cold start problem, but it's kind of similar in reverse to it. It basically means that if you have a new item, so say a new video, then you need to show it first to a fair amount of users and get some scores to be able to then recommend it to other users. And again, there are ways around it. So, for example, TikTok, what they do is they would introduce some stochasticity, so some randomness into their models, and they would show these new videos randomly to feeds of different users, try to get these scores about it. And I don't have like a classical demo, because demos there can be things that can go wrong with demos. I opted to record a running system. So here it is running these models, but if somebody is curious, then I also created a repository with these concepts. So there's a TensorFlow model, which basically does what we have discussed. It's a collaborative filtering model, and then there is some Rust code to basically run it on like small subset of randomly generated users. For the curious, there's some instructions how to install TensorFlow and how to compile and run the model. And yeah, if there's any questions, very happy to answer. Thank you.
Very good. Thank you so much, Filip. If anyone has any questions, feel free to unmute and ask away.
Actually, I do have a question.
Sure.
You had mentioned earlier in your presentation about, I think it was videos watched or videos clicked, videos liked, and then you can optimize for different things like engagement or what was the other one?
Monetization, yeah.
Exactly. Yeah, exactly. This is the slide. That is probably a whole science unto itself. Is there any place where we can get like kind of more information on how an algorithm like that might work?
Yeah, so I mean, it works fairly similarly to backpropagation in neural networks. So that's a pretty good start.
Okay.
Because that's exactly what neural network, it's a graph, right? You have some inputs, you have some nodes, you have some hidden nodes, and basically backpropagation is a type of learning algorithm where you shoot these inputs, right? You get the outputs, and then if we're talking about your training data set, you tweak the weights on the graph. And that's pretty much that's even way simpler than that.
Okay.
Just a problem of you have some type of fitness function, so something that you want to optimize for, and then your problem becomes a problem of optimizing these weights to maximize that fitness function. Really
okay.
Regression algorithms that are also about that.
Interesting. Is that maybe something, I mean, I don't think there's like one version of an algorithm for this. It's something that evolves over time. There's something known as evolutionary programming where you kind of can evolve this.
Yes, yeah, exactly. Evolution, it's just different methods of optimization. So backpropagation is one, like you say yourself, evolutionary you have introduce some random changes. The idea being that it doesn't get stuck at these local optima.
Right.
You can always try to evolve your algorithm. Yeah.
Okay, great. Thank you. Yeah, that's interesting. Definitely.
Yeah,
Go ahead. Philip, I know you do a little bit in like the blockchain space, and I'm not like with the Substrate field of things. Are you familiar with Substrate? I just know it's built with Rust, and to be honest with you, like I still have trouble wrapping my head around it, like what the concept is with Substrate. I don't know if you know much about that or.
No, I mostly worked with Ethereum, and I worked on application level, so not that low on the protocol level. Although I dug like into AVM and being into the virtual machine of Ethereum. That's about it. But Rust, indeed, yes, like you say, Rust is kind of predominantly now. Parity, for example, has been built in Rust. It's been popularized by blockchain just because I think they had this, the advantage being everything that I've discussed, like a small runtime, efficiency, memory safety, all these things that Rust brings, and Rust was there when they were building these things, so it was kind of, I guess, a natural choice for these type of systems. Yeah.
Cool. Yeah, I've seen some people commenting on it and saying, Rust is really a really up and coming language in the blockchain space, I guess, and a lot of people moving to it for various reasons. So,
yeah.
Cool.